Okay, let's begin. Uh, Cartesian components of a Euclidean vector. Number one, find the false statement regarding a vector. A vector is invariant under translation that preserves the orientation and length. Vector is invariant when we make a translation. Translation means the length is the same and direction is the same. And when we look at the vector before and after a translation, we can always construct a parallelogram. So invariant, it doesn't change. B, if the head and tail are exchanged, then V transforms into minus V. This is a V and this is a minus V. The length is the same, the orientation is opposite. Any two equivalent vectors can occupy two sides of a parallelogram. This is a parallelogram. Two opposite sides of the parallelogram. Any two equivalent vectors are linearly independent. It is absolutely the same, and it is linearly dependent. Linearly, if A is a vector, B is a vector, we multiply numbers, scalars, so add them up. So we call this as a linear combination. Linear is just a single power. The square is a quadratic. This is a linear. And nonlinear, for example, sine x, x squared, anything else, it is a straight line. This is a linear. Linear combination equals 0. This is 0 only when x, y equals 0. Then these two are called linearly independent. Linearly independent is, for example, you use ordered set of numbers x comma y. This is a 0 comma 0 only when x equals 0 and y equals 0 simultaneously. The reason is that these x and y are components. These components of linearly independent vectors. They're the basis vectors of Cartesian coordinate E1 hat and E2 hat. Because they are linearly independent, so linear combination becomes a zero vector only when both x and y are vanishing simultaneously. That is a linearly independent vector. But for example, if I have two vectors, they are the same or linearly dependent, I can multiply x and y to make 0, and whenever I substitute y equals minus x, this is always a 0. So this indicates that x and y do not have to be 0 simultaneously, so these two are called linearly dependent. Okay, so two equivalent vectors. Equivalent vector means identical vectors, so they are always linearly dependent. It is not independent. To find the false statement regarding the sum of two vectors, A, B, A plus B form a triangle. A, B, A plus B. They form a triangle, right? A, B, and A plus B are always linearly dependent because linearly dependent If you have any question, just ask me question immediately. A plus B, A plus B, and B plus A, B plus A. They make a parallelogram. So this diagonal is the same. Say this is either A plus B or B plus A. So mathematician says it is a commutative. Commutative. You can exchange the order. Okay? This operation is commutative. However, subtraction. This is a subtraction. This is not commutative. So non-commutative.
Professor, can I ask a question?
Okay. 한국말로 해도 돼, 질문. 편하게.
이번에 B번 있잖아요.
B?
한 번만 더 설명해 주실 수 있으신가요?
Linearly independent?
예.
요거?
그 문장.
A.
예.
For example, B. Linear combination. Let's make a linear combination. X, Y, and Z. A plus B. This is a linear combination of A, B, and A plus B, right?
예.
This is a 0. I can always choose Z equals minus X, Z. For example, we can always find, for example, X plus Z A plus Y plus Z B equals 0. If they are linearly independent, this is a 0 only if X plus Z equals 0 and Y plus Z equals 0. Right?
Yeah.
We always have a solution that does not have to be the 0, because if I have X and Y only, then the only possibilities of both of them becomes 0. But there are 3 variables, so I can always choose a redundant set.
이해됐습니다. 감사합니다.
Okay.
Yes.
So in one dimension, there is only a single linearly independent vector. In 2 dimensions, there are 2. It can be either convenient choices E1, E2, but I can also make A and B, they are still linearly independent. So linearly independent is very important because I can express any vector on this plane as a linear combination of these 2 something. Understood? And these components are uniquely defined only if I choose a linearly independent set. Okay?
교수님, 그러면 혹시 그 1차원 말고 2차원, 3차원 공간에서는 그 linearly independent라는 걸 약간 수직 관계 이런 식으로 이해해도 되나요?
Perpendicular form is Cartesian. Very simple case, but it doesn't have to be this is perpendicular. This angle should not be 0. That's fine. So existence of a perpendicular component is very important. But you can still add the parallel component to find these 2. This A and this B are still linearly independent. But as soon as it becomes a parallel. These two are linearly dependent.
네.
Okay?
네네.
The
감사합니다.
reason why we study Cartesian coordinate system is very convenient. They are absolutely perpendicular. Okay? So this chapter is Cartesian components of Euclidean vector. This is a starting point, and you are very familiar with the Cartesian components from the elementary school. Sure? So anyway, the content we study in this chapter is very, very important for your future in any mathematics, any physics, any other applications of matrix and vector. In physics, vector is just the property of position. The birthplace of vector is not mathematics, but just a position. So if you have any problem in understanding this mathematical object I teach you, just remember, do not refer to mathematics textbook. Instead, just come back to your own mind and your experience with the nature. This first we begin with this any vector. Just do not think this one is a mathematical object, just a position. You just walk around, you take the taxi, and okay. Very interesting to see the vector has a very similar algebraic property. Algebra. This is sum. A plus B, A times B, A divided by B, A minus B. These are algebra. Okay, so but you're familiar with the algebra of number, but you now learn algebra of vectors. And then you extend this one to algebra of matrix. And matrix is another operation we are very familiar with. For example, rotation. Okay. Zero is additive identity, that is, this is algebra. So 1 plus 0 is 1. Whatever number you give me, I can add 0 to obtain the same thing. That this result, after this operation, the result is the same. So we say this is addition. So adjective of addition is additive. They are identical to each other. They are identical, the same. So additive identity. So 0 is called additive identity of this operation called addition. And then once you know the identity, then you might want to obtain the inverse. Inverse. B is inverse, additive inverse of A if the operation called addition is applied to A, the result is additive identity. Okay, so you cancel. This additive identity is the result. That means you cancel this front term. This term disappears to become an additive identity. So that's the reason why canceling, that is inverse. So inverse of A is called B, that is written as minus A. That can be done by just 0, I add minus A, both sides, and addition is a commutative. I can exchange the order. Let me do some stupid job. Mathematician like this. And then there are 3 pieces. Now I apply associative law. Associative law. This is not coming from mathematics. Mathematician calls this, but you just add 3 vectors. You just walk from Seoul, Busan, New York. For example, this addition, this one can be added first. So A, B, C addition can be A plus B plus C. This is B plus C. This result is identical to A plus B first. This is A plus B. And then you add C. And then C. These results are always the same. The final result, A plus B plus C, is just to connect the final head and the initial tail straightly. So this is A plus B plus C. So the process obtained these are different because this and this and these and this, they are different, but the final result is the same. So we say A plus B plus C or A plus B plus C, but they are the same. So that's the reason why I do not use a parentheses, just A plus B plus C, something like that. Okay, so using that one, finally, I obtain that minus B is the additive inverse, minus B, this one is the additive inverse of A. So magnitude of 0 is always a 1, stupid guy, this is always a 0. I can always multiply some scalar, so this, if I have a vector, then I can change the length by multiplying x, that is positive. I can flip the direction by multiplying minus 1 and change the length and the direction. So this xa, when x is less than minus 1, then the length becomes longer than the original one, and the direction is opposite. The sign of this x that is multiplied to this original vector determines the length. So if I multiply 0, then it becomes a point. Four, find the false statement regarding the scalar product. Scalar product is a number. Scalar product is a number. I have a and B, and there's a foot perpendicular. Okay, this is B, this is A, but scalar product is A times B parallel, then B parallel, or B times A parallel. What does it mean by this parallel? So A can always be decomposed into 2 pieces. That is a perpendicular to B, and let me B, A per A parallel, Understood? This A vector can be divided into two pieces as an addition. A is sum of A parallel plus A per. That means this parallel and perpendicular means relative to this vector B. Understood? In that case, scalar product is just the length of A and length of B and A's parallel component. Another way to define this is just to keep A, this is the length A, and we have B is here. B has a component perpendicular to A, and B has a component parallel to A. Understood? So scalar product is just collecting the product of the two vectors along the same direction, parallel components product. So because we just collect this parallel component, this theta is given in here, then we can always make a right triangle, and this parallel component is A cosine theta. Middle school student can compute this. So A multiplied by B parallel, or A parallel B, is this one is A times A cosine theta times B, and this one is A B cosine theta. In either way, it is always A times B times cosine theta, where A and B are the magnitudes of the two vectors. But you already watched X3, so I do not have to explain in detail. So I always tell you, we are solving these problems only in the class, but you have to watch XN very carefully. Every detail is explained in there. So you must learn it in advance very carefully. All right. A dot B is called the scalar product, and the value is product of magnitudes of the two vectors multiplied by cosine theta. And the angle between two vectors A, B, this angle theta is from, what is the minimum value of theta? Tell me. It runs from 0, and this theta does not exceed pi. So 180 degrees is the maximum value. So angle, sure, you could measure this angle 2 pi minus theta. That's fine. You will find the same result. The scalar product is a positive definite. Stupid guy. Scalar product is in this case, it is a positive. However, in this case, if angle theta is greater than right angle, then they have opposite component. So projection, this projection, the parallel component projection is opposite. This one, they are opposite. So in that case, it becomes a negative. So this scalar product becomes a negative. This is positive. It is in the range minus minus A times B, and the maximum value is A times B. Okay, A hat is a vector divided by its own magnitude, and its magnitude is scalar product to itself squared, because we say A dot A is A cosine 0. Cosine 0 is 1. So we can say A dot A equals absolute value of A squared, right? We now take the square root. Because it's a positive, we define A vector magnitude. We always express the magnitude of vector as a square root of A vector dot A. So simply we say A vector squared. This one means scalar product with itself. Okay, everything is clear. So we know this. A times A hat. A times A hat. This is the magnitude of A. A subtracted by I have a I have a unit vector A hat that is along the direction. A equals actually the same as A hat dot A, because this one gives the magnitude. So the reason is that A hat is defined by A divided by its own magnitude. We multiply this one both sides, we will find that A absolute value, A hat equals A vector, right? It's very simple. So using that one, what we can do is A minus A hat, A vector, A hat. What is that? Because it is identical to A, it is a zero vector. For example, in 2 dimensions, we have E1 hat, E2 hat. That means that this is along the x-axis, and magnitude equals 1. This one also magnitude is 1. So I can draw a circle centered at the origin, and the only difference between them is the direction. Magnitude is 1. Now we find that E1 and E2 are perpendicular. So it is a very simple E1 hat dot E1 hat equals E1 magnitude cosine 0. This is 1. E2 hat dot E2 hat also 1. Extend it into 3 dimensions. E3 hat dot E3 hat 1. And then why don't you compute this one? E1 hat dot E2 hat, E1 hat magnitude, E2 hat magnitude, cosine half a pi. They are right angle. This is always a 0. Aha. Descartes is very clever. Combining everything together, EI hat dot EJ hat equals either 1 or 0. It is 1 only if I equals j equals 1 or 2 or 3. Everything else, you can choose 1, 2, 3. You can choose 1, 2, 3. So in the multiplication table, you have 9 times 9, right? 81, you know. 9 by 9, 1, 2, 3 to 9, 1, 2, 3 to 9. You have a multiplication table in elementary school. Perhaps you learned it at 5 before entering the elementary school. We can make a multiplication table for E1, E2, E3, E1, E2, E3. And we write E1 hat dot EI hat dot EJ hat. So this represents I, this represents Z. So tell me your answer. E1 dot E1, what is that?
1,
2, 2,
1,
1,
3, 3,
1,
1, 2,
0,
2, 1,
0,
1, 3.
0.
This is called 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay? Right? This array. This is a multiplication table of Cartesian unit basis vectors. Okay? We write this one as
교수님,
음,
그 혹시 100, 010, 001 적으신 거 있잖아요.
음.
이게 그 단일 행렬이라는 연관이 있는 건가요?
좀 요거하고 요거를 여기다 갖다 옮겨 놓은 거예요. 주방하고.
네.
이게 해시여야지 일이 되지. 해시 아니면 일이 안 되지.
네.
음.
알겠습니다.
Okay, so we write this one, scalar product of any two Cartesian basis vectors. We just define this delta I, j. This is just definition, just the name of this one. It's difficult to write, so simply we write this one as delta ij, and collection of delta ij's, that means delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, delta 2, 2, 2, 3, delta 3, 1, delta 3, 2, delta 3, 3. So using collection is 9 numbers, as we introduce a symbol, simple symbol. So 1, to distinguish it from just the number 1, is and open a big parenthesis, close the parenthesis, put these numbers. And any element inside this parenthesis is a delta ij. That means I, this is I equals 1, I equals 2, I equals 3, j equals 1, j equals 2, j equals 3. So just to remember, this is nothing but the multiplication table of the Cartesian unit basis vector. Okay, so this one we name it as identity 3 by 3, 3 by 3. So we have first row, second row, and third row, column, second column, and third column. So 3 by 3 identity matrix. This is the origin of a matrix. The origin of matrix is just a multiplication table of unit Cartesian basis vector. Understood? Now, let us compute the scalar product of two vectors, A dot B. It is A1, E1 hat, A2, E2 hat, A3, E3 hat, right? Dot, it's too long. B1, E1 hat, B2, E2 hat, B3, E3 hat. Multiplication, expansion of this multiplication with 3 by 3, 9 terms. Okay? Among 9 terms, because 1, 1, 1, 0, 0, 0, 0, 0, 0, remember this multiplication table. Using multiplication table, the only surviving terms are 1, 1, 2, 2, 3, 3. Understood? E1 dot E2, E1 dot E3, all vanishes. Okay? So the only surviving terms is A1, B1, A2, B2, A3, B3. Only when you use Descartes' coordinate system, Cartesian coordinate. Cartesian coordinates is very useful. And then, why don't we express this one? This is a three-dimensional, 1, 2, 3. In 2 dimension, you erase the third component, okay? In 2 dimension, this multiplication table is just simply this, 2 by 2. We introduce a simple expression. Just write this one as A1, A2, A3 without comma, a B1, B2, B3. Looks better. Need more space, but looks better. And just memorize. This is we promise to say this one is just multiply these two, multiply these two, multiply these two, and add them up. This one is, this expression is written in the form. So this is just a vocabulary. You don't have to understand, just memorize. You write this one as this. So we say represent matrix representation of a Cartesian coordinate. So in high school, you learned x comma y comma z, or x comma y in middle school. You just write these Cartesian coordinates, basically x, y, z. And then if you want to compute the scalar product of two vectors in terms of Cartesian coordinates, you remember these x, y, z are not vectors. X, y, z is Cartesian components, y, E2 hat, z, E3 hat. This one is hidden in here. But because I know the multiplication table, let's forget about the basis vectors. Just make use of the Cartesian components. Then we call this as a matrix representation of a Cartesian coordinates, so x, y, z. Just these are coordinates. Scalar product, then I can write it first, second, third Cartesian component as a row. On the right side, first, second, third Cartesian component as b vector as a column, and multiplication is this matrix representation is just multiply the first elements, find the product of the second elements, and find the product of the third elements, and add them up. This is the scalar product. And this is the beginning of the matrix. Okay? Matrix is not created independently. It is just it just came from the scalar product of two Euclidean vectors in terms of Cartesian coordinates, remember. And why don't we, perhaps you didn't study this X3 at all, but you have to listen carefully. So I have explained every detail in here, but you just play and do not watch. That's the problem. Please watch everything. Everything is written in here. Okay? All right. So this is the beginning, and this one can be extended to the matrix multiplication. Why, for example, I have A dot B, wait a second, A dot some vector, B dot some vector, C dot some vector. I have three scalar products. Let me say this is C1 and C2 and C3. I want to find a vectors that satisfies these three equations. Then I can write it x1, x2, x3 as a column, and this one a1, a2, a3, b1, b2, b3, c1, c2, c3. Let me write it d1, d2, d3. This one is d1, d2, d3. This is a matrix equation. The first row multiplied by this x1 to 3, it represents the first equation. This equation is represented by multiplication of these two to find this. And this equation is a multiplication of this and this. Okay, so matrix is nothing but a different representation of scalar product. All right. So I write it as this comes from meter. Meter is a measure. So metric tensor is A dot B. How can I define a scalar product in terms of Cartesian coordinates? This one was let me just simply write in 2 dimensions. This one was the scalar product in 2 dimensions. However, this one can also be written in this form. I need some space. Oh. B1, B2. Just copy the first one, and why don't we multiply these two? What's that? 1, 0, B1, B2. This was 1 times B plus 0 times B2. Here's a B1, right? So B1. 0, 1, B1, B2. 0, B1 plus 1, B2. B2. That's the reason why we call this one as identity matrix. Multiplication of an identity matrix to any vector is itself. They are the same. I don't change any result. So that's the reason why A1, A2, A3, B1, B2, B3, that is actually the scalar product of the two Euclidean vectors. This is identical to A1, A2, A3, 1, 1, 1, 0, 0, 0, 0, 0, 0, B1, B2, B3. So this identity matrix is a metric tensor of this Euclidean space. Anyway, we need to go ahead. Find the false statement regarding the completeness relation for the unit Cartesian basis vectors. Completeness relation. This one is a one-dimensional case. Is identity, right? A must be expressed in terms of single basis vector. In 2 dimensions, I need 2 basis vectors, and each Cartesian components, you see, A is A1, E1, A2, E2, A3, E3. What is A1? How can I find A1? Just multiply the unit vector E1 in here. Then E1 kills 2, 3 components, and what I get is A1 only. So this expression is nothing but E1 hat E1, E2 hat A2, something like that. In 3 dimensions, it is E1 hat A1, E2 hat A2, E3 hat A3. But everything can be obtained. A1 equals a vector scalar product E1 hat. A2 equals a vector dot E2 hat. A3 equals a vector E3 hat, and so on. And it can even be extended in arbitrary dimension. Although in our displacement in 3-dimensional space, we stop at n equals 3, but in principle, we can extend this to n-dimensional case. So later in this semester, we have to extend this idea to the n-dimensional Euclidean space. So when we consider, when we study the interaction of molecules. 9, find a false statement regarding the basis vectors. Let me just pass it as a very simple problem. Okay. The rotation is very important. We will find rotation in the next 2 lectures, but it is just a preview. All right. In 3 dimensions, sphere is defined by any position, any point on the surface of a sphere. This is the origin. We have the x vector, and this x vector has a Cartesian coordinate x1, x2, and x3 in matrix representation. Understood? And because it's a sphere, sum of squares should be constant. That is a radius square, right? Understood? X squared plus y squared plus z squared must be the same as r squared. This is an equation of a sphere. All right, so this is a way how to write down the coordinate in three-dimensional space. So we have a z-axis from the center to the North Pole, and we have South Pole. Why don't we choose the angle theta? This is a polar angle, and this is the point on the surface. This is a radius r. You will find this perpendicular distance from this rotational axis, this axis connecting north and south poles. This is a right angle. This is r, and this angle is the theta. What is that? This length is r sine theta. Okay, so we have r, just the cross-sectional view. This is the theta. Wait a second. R cosine theta. And this is r sine theta. Okay? So this z component is r cosine theta. And this perpendicular component is r sine theta. And in here, if you look at this part of cross-section, if you look at this part of cross-section, you will find this is r sine theta. And then this is a plane parallel to xy. This is x and y and z axis. This because this xy component square is this one square, r square sine square theta. Okay, z square equals r square cosine square theta. Because of this, we can finally parameterize the three-dimensional, the Euclidean coordinates, the Cartesian coordinates, in terms of the z component is r cosine theta. This is x3, and the x component is r sine theta multiplied by cosine phi. X2, that is x, that is y, is r sine theta sine phi. So theta and phi, theta, this is a theta, this is a phi. So phi is related to longitude of the Earth. Theta is related to the latitude. We divide, we make a grid, and from the equator we measure the angle. So we are living 37 point something north from the equator. And then phi determines, phi is called azimuthal angle. And theta is called polar angle. All right, we have 10 minutes to go. Anyway, this angle, this polar coordinate will appear repeatedly. So even though you're not familiar with these polar coordinates right now, but you will be familiar with this in the end. It will be repeated. Consider two vectors A and B whose matrix representation, the Cartesian unit basis vector, are so magnitude of A is 1. So this is just A1, A2, A3, right? This. So magnitude is a square root of A squared, right? So we first compute the square. How can I compute the square? A square is the row. This is A1, A2, A3. Making this column to convert this column to a row is called transpose. Transpose. Flip this one as a row. So A1, A2, A3. If we multiply this, the answer is A1 squared, A2 squared plus A3 squared, right? So cosine squared plus sine squared, that is 1. In a similar manner, B squared is a minus sine squared and cosine squared, that is again 1. Aha, these two vectors represent unit vectors. Perpendicular, okay. So scalar product of these two, just copy cosine, sine, 0. B copy this one, minus sine, cosine, 0. Multiply. That is sine, cosine, but negative sign. This one, same but positive sign. This 0. The answer is 0. Aha, scalar product is 0. They are perpendicular to each other. All right? Angle between B and E1. Aha. Then what we need to compute is just E1 hat dot B. E1 hat, simple. 1, 0, 0. B, what is B? Minus sine theta, cosine theta, 0. Multiply. Minus sine theta. Aha, minus theta is not cosine theta. Cosine something is a minus sine theta. You can find that this is a half of pi minus theta. 12. You do this job, it is a simple. E2 hat, this 0. E1 hat, E1, 0, 0. E2 hat, 0, 1, 0. E3 hat, 0, 0, 1. So using this matrix representation and these, you can compute E2 hat dot A, then E2 transpose 0, 1, 0. A cosine sine 0. Multiply. This one 0, this one is sine. In this manner, you can compute. All right? So these are just a repetition of the same objects. We have 3 vectors, and actually this one is later you will find that this is E1 and this is E2. And we have another unit vector that makes an angle theta with the E1 hat, so ER hat. is a radial vector in polar coordinate system. And this one makes an angle. This one is E1 hat cosine plus E2 hat sine. Why? You can do this because this is angle theta. This one has a component. This is component along the E1. And what is the angle? What is the angle? Cosine. So this is cosine. What is this angle? This is half of pi minus the theta. So cosine half of pi minus theta equals sine theta. That's the reason why this one is sine theta. So we introduce, this is old E1 and E2, but this I have redefined this one as a E1 and E2, something like that. So when this one are given, this is just a training of multiplication and matrix representation. Just copy this one as a row, 1, 1. Copy this one as a column and multiply. The result is 1. 2, 2. This one is 2, 2, 2. Multiply to find this result. 1 and 2. So 1 and 2. Multiply these results. Minus in here appears, plus they cancel. That means scalar product is a 0 and they are of length 1. The result says E1 and E2 are perpendicular to each other, right? Again, the E3 is here. I just copy E3. For example, E1 dot E3. Cosine, sine is 0, 0, 0, 1. Multiply is 0. So again, E3 and E1 are perpendicular to each other. Now we have two orthogonal vectors. We just learned that cosine sine and minus sine cosine, they are perpendicular to each other. You remember cosine sine minus sine cosine, multiply, they cancel. So these two vectors are perpendicular to each other. Let me just copy these perpendicular vectors as two columns of a matrix. And what about the transpose? Transpose is changing this column as a row. The transpose, changing this column as a row. Changing second column as a second row. I copied this. And this A transpose is just replacing columns into rows, right? So A transpose multiplied by A. A transpose is here. I just copied the here, and A is copied in here. Why don't we multiply these two? This itself, scalar product of itself, it is 1. These, they cancel because this one represents E1 and this one represents E2, and this one represents E1 and E2. E1 dot E1 is 1, E2 dot E1 0. In a similar manner, E1 dot E2 equals 0, and E2 dot E2 equals 1. Aha, is identity matrix. In a similar manner, I can flip the order to find the same result. This is identity matrix. Multiply something different, you obtain identity. Then this one is called inverse. Okay? A times 1 over A equals for any A that is not equals to 0, it is 1. We say this is inverse. In the matrix case, again, if you multiply two matrices, the final result is identity matrix, then we say this one is an inverse matrix. But very strange, the inverse matrix is compute a very simple way, that is, just flip the column as a row. This special case, this is called the orthogonal matrix. Why? We have E1, E2, E3. They are Cartesian basis vectors satisfying EI dot EJ equals product delta. It is a 1, 1, 1, 0, 0, 0. The reason is that they are orthogonal and everything has a magnitude 1. In that case, inverse matrix computation is trivial. You don't have to worry about it, just flip the column into row, column into row. I have found the inverse matrix. What is inverse matrix? Multiply two matrices, you have just identity matrix. So after that, they are exactly carbon copy of the calculations. Let me tell you, there are typos. B, it should be 17, B and C. It should be replaced with B vector. All right, so these are extensions. So you can, if you have some problem in solving these, just ask me questions through the email or in the next class. Okay, that's it for today. 질문이 있는 사람은 남고 갈 사람은 가세요.
교수님, 20번에
음,
B에서 B번 문항에서
음,
행렬 11 빼기 코사인 세타 플러스 사인 세타 행렬 코사인 세타 사인 세타 이거를 어떻게 하는 거죠? 이건 빼기가 중간에 빼기가 네.
빼기잖아.
네.
얘는 요걸 얘를 1 빼기 코사인 플러스 사인 코사인 1 빼기 코사인 플러스 사인이잖아.
아, 이렇게 계산하는 거야.
이거 넘버니까. 이건 매트릭스가 아니야.
네, 알고 그건 알고 있습니다.
그러니까 이 매트릭스는 카테시안, 우리가 그 카테시안 베이시스 벡터를 왜 배우냐를 생각하면 되는데, 이게 어디에서 왔냐면 A 벡터를 A1, E1 hat, A2, E2 hat 이렇게 해서 했는데 얘를 날리고 요것만 카피해서 온 거잖아.
네, 그렇죠. 네.
그러니까 얘네들의 연산을 하고 있는 거거든. 그런데 이제 여기 요게 사실은 얻은 거에서 어떤 A 벡터 빼기 뭐 2배 B 뭐 이런 걸 계산하라고 했는데 여기에서는 이걸 다 써준다면 A1, E1 hat, A2, E2 hat 그리고 얘는 마이너스 2배 B 이렇게 하면 2배 B1, E1 hat, B2, E2 이게 쓰기 귀찮아서 만든 게 매트릭스예요. 그럼 이걸 여기다 이제 전개를 해서 A1 빼기 2배 B1 괄호하고 E1 hat 이런 식으로 쓸 수 있는 거잖아.
아, 이렇게 해서 그렇게 되는군요. 아, 알겠습니다.
그렇죠. 그러니까 여기에 막 어지러울 때는 이게 어디에서 왔는가를 우리 처음에 쓸 때를 생각해 보면 되게 쉬워져.
아, 감사합니다. 예. 네, 그럼
그런
이해됐습니다.
이유로 우리는 카테시안 코디네이트에 익숙해져야 하고, 그러니까 이제 가면 갈수록 이게 오리진을 까먹으면 수학을 외울 것이 너무 많은데 이게 이렇게 지저분하기 때문에 간단하게 쓰는 거지 매트릭스가 복잡한 게 아니에요. 매트릭스 써서 복잡해지면 그거는 문제를 잘못 푼 거죠.
예, 이해됐습니다.
오케이.
네, 감사합니다.
교수님,
음,
12번에 C에 A 벡터랑 B 벡터가
잠깐만. 12번에
A 벡터랑 B 벡터가 평행하다는 걸 어떻게 계산할 수가 있어요?
패러렐 A 닷 B를 하면 A, B 코사인 세타 이렇게 될 거 아니야. 그제?
네,
그러니까 세타가 코사인 세타를 계산하라는 거지. 코사인 세타가 1이라는 걸 보이라는 거지.
네.
코사인 세타를 어떻게 계산해? A다 B를 계산하고 그것을 이걸로 나눠주라는 거지. 여기 A 닷 B가 뭐지? 0이잖아.
네.
0이면 이게 패러렐해? 퍼펜디큘러지? 그럼 이게 틀린 거겠지.
아, 그렇구나. 맞는 선지인 줄 알았어요.
음. 이게 틀린 게 하나씩 있어줘야지 사람이 생각을 하게 돼. 다 맞으면 이걸 이제 안 하고 그런 걸 외우려고 하는데 그래서 일부러 그 하나씩 틀린 거를 넣어준 거야.
네, 감사합니다.
예.